Hello everyone, we will see B plus tree indexing. This is the most commonly used in your DBMS to represent your file system in the organized manner by using some kind of searching, insertion and deletions improvement. So why we are only going for B plus tree means it's a well balanced tree compared with your B tree representations. So you can represent multiple pointers related link or by using this kind of representation. The index will be produced for multi-value representation. There is a linkage between your nodes. So this is a root node which is going to be created, and the children nodes will have some kind of reference pointers. So where the data is going to be stored means at the end of your leaf nodes, all the leaf nodes are going to be pointing to the record related information. So why this hierarchical way for produced means in order to find your records in the effective manner, we are going to search them or search them based upon the values which are indexed in your root levels. So for example, if you want to delete, if you want to insert the data 99, so most probably it is going to be left side of your 100 element. Why? Because the smaller elements are going to be kept this side, so larger elements are going to be pointed to this side. So now I am having only smaller elements to this side, so maybe I can insert my 99 element to the left side. Instead of searching all the indexes, instead of touching all the elements, directly I am pointing to nearby address locations. So this is the beauty we have in your B plus tree. So we'll try to trace them, whether what are the best things we can do with your B plus index tree. So before entering into them, there are several kind of examples we have with which will work with a string based representation, because small letters, alphabetical order is there. So by using that alphabetical order also we can do ordering your elements. So why we need to go for only B plus representation means, so there is some kind of advantages you can see on the screen. So it's a self-balancing representation. No need to do anything. Automatically it will be balancing after insertion and deletions were happening in your tree representation. And whenever you are constructing your tree representation, it never loses its balance. So it is following some kind of constraints while inserting your data. So if it is not being in the constraints, again you need to split the data into multiple shallow parts. So that is a beauty we are having. So this B plus tree is having a multi-level representations, because in each level you can represent your data, and each level is consisting some kind of constraint based children. So we could maintain only a specific children to the root node. So not more than that we can represent. So and while inserting your data into B plus tree, we should follow some kind of order. So without an ascending order or descending order, you could not able to insert your data into your database. So basically we should always follow ordered and as well as balanced structure for your insertions and deletions. So due to this we can get some kind of friendly approach, because by using this kind of instead of loading all the elements, we can load only few elements which are useful for us. By using them we can trace out that where your data is going to be represented, right? So we have some kind of special representation. It's based upon disk orientation. We can store multiple disks to your B plus tree representation at your children's. While constructing your children nodes and leaf nodes, we need to have some kind of structure. The structure is going to be looks like this. So for example, if I'm having a data element, this data element may consist of pointer 1 and pointer 2. So always your data is going to be kept like this. Left side pointer, right side pointer. Left side pointer is going to point to the smallest elements which are existing in your database, and right side is going to be represented for largest elements. This were large, this were small. So always it follows the structure to represent your data. Always your leaf nodes are very essential for your root node, and because with this we can represent all your physical notations like your data or your file systems. So now there are several kind of operations we can perform by using your B plus tree. Either you can do insert, you can do delete, you can do searching. These are the basic representations we have. Whenever you are searching or whenever you are inserting, it is always identifying them by using this order. For example, if you are looking for a larger element, it will move to your right side. If you are searching for the smallest element, it will move to the left side. Only one side representation will be useful. So due to this, your operations becomes more effective. in your B plus tree. So most probably your applications like DBMS is only using your B plus tree. There are several other notations we have, but still most of the B plus database related applications were constructed this indexing by using your B plus tree notations. So now we'll try to see some kind of conditions which are existing for your B plus tree constructions. So whenever you want to produce some kind of B plus tree representation on your data elements, must and should you have to know that what is going to be your root node and how much data is going to be represented in your data. For example, I want to make n elements. N element should not sit in your root node, and this root node is going to be split into two different kind of parts. So depends on your data variable, your data has to be divided. So to do all these things, we should follow some kind of constraints in this particular representations. Whenever you are going to create any kind of root node, so this node is for example, if my order size or pointer size is going to be 4, just assume that. So if you are having like this, you can create a maximum number of children for your tree is 4. See, try to assume that there are several elements we have for this tree creation. If you have started with a root node may consist many number of references. So this root node can hold up to 4 references. So it means what we are creating some kind of children's 1, 2 and 3 and 4. So maximum number is 4, and you can create your number of elements, number of children for your each level is going to be 4, and minimum children you maintain by n by 2. It should consist at least 2 representation. For example, if you are having 4 elements, 4 by 2, so you are having left node and as well as right node, so then only you can say that it's a balanced tree. So after that, if whatever the node you are creating, inside this node you need to take place of data and as well as pointer. So how many keys I can place that holds data, so that is depends on your n minus 1. Maximum I can use n minus 1. For example, if I am having n, so I can store only n minus 1, 3. So 3 will be treated as key elements, and each key consists with some kind of pointers to it. For example, I'm having like this node key 1 and key 2, and one more is key 3. Every key side there is a left pointer, right pointer, and left pointer, right pointer, and one more is left pointer, right pointer. Like this you can create a pointers. So your node is consisting keys, along with the keys you are having some kind of pointers, so which are pointing to your leaf nodes. So minimum number of elements should exist in your node is that is going to be n by 2 minus 1. So for example, if you are having 4 by 2, order is 4 by 2 is 2 minus 1 1. Only one element should exist in your node. So without this, say for example, root node like this, it was divided and it should consist 2 elements. This side empty elements are there, so we could not able to represent like this, because to make it balance, at least we should consist one element to your left right side. So next, mid element in n by 2 plus 1. So if you are going to find, for example, I want to do some kind of splitting. So to find the splittings, so we need to go with n by 2 plus 1. For example, 4 elements, 4 by 2, that is going to be 2, 2 plus 1, 3. So like that you need to create your tree representations in your B plus tree. So we'll try to trace out that how these things are going to be happen. First we'll go with an example of very simple one, and by following this kind of constraints we'll construct your tree. So we'll see that we'll go with a very simple example. So this is how it is going to be represented. So our elements are this n by 3, and we have some kind of several constraints. So we need to follow all these constraints to implement your tree. So first, as per this n equal to pointer number 3. So now whenever you are going to create a root node, so that should consist how many number of elements. So the maximum number of elements are going to be n minus 1, minimum number of elements are going to be n by 2 minus 1. So there I have maximum numbers in this particular node is 3 minus 1, so it should be 2 we can store in a single node. So whenever it is exceeding this element, so you need to split that particular node into two different kind of nodes, either left and right side. So first I have an element called 15. So first I'll try to insert that 15 will be into your segment. So now I have one more empty space, that is with to insert the next element. So if I'm going to insert the element, so then it should be swap your elements. 5 is first, next is 15. So now this node is consisting two elements, that is reaching a maximum number of keys which are going to be stored in your every node. So after that your user wants to insert element called 20. So now if I want to insert the 20 into this node, so the node is already filled, so we could not able to insert the element. So then we need to go for splitting of your elements into two childrens. So this split will be happening based upon 3 by 2 plus 1. For example, 3 is your number of elements, and by 2 that is going to be 1. 1 plus 1, it leads to be second element. So this is 1, 2, 3. So my second element is going to be what? 15. So my 15 node will become a root node. So 1 and 5. So now the pointers of left and right. So now left side is pointing to the smallest elements which are than 15. So first slot is going to be filled with 15. Second, I am using some kind of linkerless connectivity between your children. So I need to maintain the reference of your parent element. So this is the parent representation, right? So next I am having an element called 20. So these elements are going to be larger and these elements are going to be smaller. So next I have an element called 10. 10 is going to be inserted into my tree. So while inserting an element, it is going to be compared with the key. So whether it is going to be fall to left side or it is fall to right side. So 15, 10. So 10 is going to be inserting now. So it is smaller element. So obviously it is going to be filled the left side representation because there is an empty space we have. And after that you are going to insert a next element called 25. So if you are going to insert this into list, the list is maximum number is 2. So we could not able to hold all these three values here. So then we need to reorganize your tree representation. So now whenever you are doing this, just assume that whenever you are doing this, so one of the element will be either push towards to up. Why? Because there is an empty space will exist in your root node. If there is no empty space, you can split your elements into two children. So by using some kind of self balance. So as per this notation, so I need to find the mid element. Mid element is going to be this. This will be pushed to top. So now 15 and one more is 20 will be my root nodes. Left side elements are going to be 5 and 10. And is there any intermediate elements are existing? No. And after 20 there are some kind of elements which are going to be exist. So 15 is for only reference variable because I need to maintain the connectivity between this. And next 20 is that 20 will be exist 20 reference variable and one more is 25. So I inserted 25 successfully into this node. So now I am going to split this. So sorry, I am going to insert one more element 30. So where should I insert this 30? So there is no opportunity for left side, middle there is an opportunity, but the value is larger than this. So now I am going to move your 30 to this side. So while inserting your 30 into this list, so there is no swapping will be happening because already we are in the order. So there is a mid element is this. So now it is going to be pushed to the next list because whatever the element is there, it is going to be moved to this. So now if I am going to move this to this 15, 20, 25, again the split will be happen. Why? Because we could not able to place 3 elements. I can place only 2 elements in my root node. So now the split will be happen based upon the mid value. So 20 will be represented here, and after that the split is going to consist the elements of 15, next 20, 25. So I have a root node. So this 15 may have one more elements, that is either 5 and as well as 10, and next there is no elements which exist. So 20 and 15, this side there are no more smaller elements, and 25, yes, there is one more element I need to create, that is with a 30. 25 is the reference variable and one more is 30. So this is the representation we are going to do for your B plus tree notation. So we have seen 3-elemented notation. We will see how this 4th element notation is going to be works with all your constraints. So now see this, we have childrens of 4. So now these keys are going to be n minus 1. So it means what? 3 elements. So in my root parent tree, I can insert 3 data elements. So first I'll insert 2, next I'll insert 3, and next I'll insert 5. Again I want to insert 7 into this root node. Root node is already filled, so I could not able to place 7. So now the split will be happen based upon the mid value. So 4 by 2 plus 1. So that is going to be 2 plus 1, 3. Third element is going to be represented as a root, and this node is going to consist 2 more empty spaces. And first left side is going to consist 2 and 3, one more empty space here. And next we are having 5 and one more is 7. So left side your elements are going to be represented as 7. So again there is one more empty space at your 5, 7 node, right? So now again I'll insert one more element that is called as 11. So I can insert happily 11. So till this particular point 2 is inserted, 3 is inserted, 5 is inserted, and 7 is also inserted. So now I want to insert 11. 11 is also successfully inserted, and 17. So now if I am going to do insert 17, already all in sorted order. So now I need to find the mid element. Mid element is going to be 11, and 11 will be pushed towards your root node. So now it should be represented 5, and one more is 11. So this root node may consist 2 and 3, and after this you are having your 5 and as well as 7. So one empty space will be available here. And coming to the 11, 11 is also having one reference variable, one is for 17, and one more empty space will exist in your table. Now I am going to insert 19, 19 happily inserted, and next I need to insert 23. So 23 means this should be splitted into we could not able to place 23 here, so we could split this node, and we need to move one element to your parent side. Why? Because parent is having some kind of empty space. If it is not having empty space, then it is going to be divided into 2 subparts. Now what is this constraints we are having? 5 and 11, and one more is 19. Then see this. So now we are having 2, 3 empty space, and now we have 5 and 7. This is one more pointer, and 11 we are having 11 and 17. So we could not able to place 19 here. So we have one more empty space, and next after 19, sorry. Right. After 19, so we could able to place 19 and as well as 23. One more empty space will be exist. So now see this, your tree notations 23 is filled, and we are going to insert 29. So now I am going to insert one more element 29. So 3 details were filled, 3 notations were filled. So now there is no problem for us. So now I am going to move 31 to this tree notation. So if you want to insert 31, so again you need to insert 31 into this space here, but there is no possibility. So we need to push one element to the top node. So now I am going to insert this 29 into this particular list. Now 29 is unable to sit here. So now I am going to make 19 as the root node. Right. So 19 will become the parent node. So now 19 will sit here, and the remaining there is empty spaces will be have. The smaller element should be left side. So as per this 5 and 11 will be broken into one side, and next which are represented greater than 19, which should sit this side. So the reference variable 19 will be as usual, and the next the element which is going to be represented here, you need to check. For your left side 5, 11, so there is a connectivity as per earlier tree, 2, 3 and empty space, and between 5 and 11 there is one more root node 5, 11. So after 11 there are no more elements which exist in your table, so we could not able to take place them here. Coming to right side, 19 is the reference variable from your parent. Next, which element has to be takes place here? So as per our split, 19 is pushed here, and there is a split between these elements. So now 29 takes place here, right? So then this will be divided into two subtrees, 23, and one more is going to be after 29 we have an element called 31. So there is two different nodes will be generated. So all your children are having some kind of data. So this is how your tree representations are going to be generated in your B plus tree. So all are internally connected. Why? Because 2, 3, 5, 7 and you are having after 11, 19, 23, 29, 31. So everything is individually connected. Your children nodes are going to be individually connected every time. So this is how your B plus tree constructions will be happen in your DBMS. Right. That's it.